Evet, değerli katılımcılar, hoş geldiniz tekrar. Bugün öğleden sonra keynote'una. 5. keynote'umuz aslında en ilginçlerinden biri benim açımdan. Hitay Özbay hocamız aramızda. Ben kendisini takdim edeyim. Hitay Özbay, Bilkent Üniversitesi Elektrik Elektronik Mühendisliği bölümünde profesör ve Ankara'da görev yapıyor şu anda. BS, Master ve PhD derecelerini Orta Doğu Teknik Üniversitesi'nden, McGill Üniversitesi'nden ve Minnesota Üniversitesi'nden aldı. Önceki akademik görevler arasında Rhode Island Üniversitesi ve Ohio State Üniversitesi'nde aldığı görevler var. Burada elektrik bilgisayar mühendisliği profesörü olarak Bilkent Üniversitesi'ne katılmadan önce görev yapmıştı. Ayrıca 2009-2010 yıllarında Fransa'da INRIA'da visiting öğretim üyesi olarak görev yapmıştı. Hitay Hoca IEEE Kontrol Sistemleri Topluluğu'nun yönetim kurulu üyeliğini yapmıştır 2017-2019 arasında. Avrupa Kontrol Derneği Genel Kurulu üyeliğini 2013-2019 yılları arasında Türkiye'yi temsilen yapmıştır. Birçok dergide IEEE Transactions on Automatic Control, CM Journal on Control and Optimization ve Automatica'da dergi editörlükleri yapmıştır. Kontrol alanında dünya çapında bir misafirimiz var bugün. IFAC, Ağlı Kontrol Sistemleri, Network Kontrol Sistemleri Teknik Komitesi'nin başkan yardımcılığını 6 yıl boyunca yapmış. Şu anda da IFAC Linear Control Systems Technical Committee'nin başkan yardımcısı ve bir IEEE Fellow, diğer konuşmacılarımız gibi. Kendisini büyük bir zevkle sahneye davet ediyorum. Buyurun hocam.
Çok teşekkürler. Öncelikle nazik davetiniz için. Onur Hocam, Bayo'yu nereden aldınız bilmiyorum ama belki de benim web sitesinde updated değil. Şu anda Linear System'ın başkan yardımcılığını yapmıyorum. 2 senedir bitti o iş, evet. Ondan sonra bir de şu anda aslında aynı zamanda University of California Davis'te visiting profesör olarak da çalışıyorum. Gerçi o Kasım'a kadar devam edecek ama şu anda fiziksel olarak buradayım. Konuşmamı İngilizce yapmayı tercih ettim çünkü Türkçeyi parçalamak istemiyorum. Kusura bakmayın. Okay. Today we are going to deal with time delay systems and time delay systems in networked control systems. So this is the outline of my talk. Look, where is it? Yeah. The main part of the talk is going to be on time delay systems and some robust control problems related to time delay systems. But before we come to this point, I'm going to introduce some examples where you see these kind of problems. And I hope that you will appreciate the kind of things we are doing for applications also. This is not just theory. When I teach feedback control course, the students complain that this is too mathematical. Where are we going to see this? So I throw them a bunch of examples and then now from here on, cope with the mathematics, okay? So that type of talk this is going to be. First, lots of pictures, examples, and then some technical stuff, mathematics. In the second part, this is going to be very short. I'm going to show you some recent results and discuss some open problems related to that. Okay, so the first part, cyber physical systems and network control systems. And they contain time delays, okay? So I abbreviate time delay systems with TDS. And I'm particularly interested in robust control of time delay systems. So what is cyber physical system? I don't think I need explanation for this audience. Anything that is connected and controlled over the network, bunch of complex systems fall into the category of cyber physical systems. So the communication is done over the internet. And these are examples of network control systems, okay? And time delays appear in these kind of systems because of physical constraints. So what are physical constraints? Typically, mathematical models of physical systems that you need to control contain time delay. That's fine. But non-collocation of actuation and sensing, which happens in cyber-physical systems actually quite often, cause time delays. Computation time, transmission, and transport delays are existent. And also when you have a human-machine interaction, so human reaction time, it is finite, it is a time delay. Okay, so these are examples of networked control systems with delays. Okay, lots of biological systems, example, telerobotics, communication networks, smart grids, etc. There are also biology applications, gene regulatory networks, for example, they do contain time delays. Population dynamics, they do contain time delay models. By the way, we have published papers on all of this stuff, but I am going to concentrate on control over networks, which may interest most people here because it's a signal processing, communication, information theory focus, okay? So in this system, we have a plant, okay, physical system, and it is controlled over the network by a controller which is not physically attached to it. Okay, the communication between the two is done over a network. So the controller sends a command signal and it gets to the physical plant as U of t. So the command signal is UC, and similarly the sensor output Y reaches the controller as YM. The problem is that these two are not exactly the same at all times. Okay? So, performance of the network control system, this control system, take any performance metrics in control theory, is adversely affected by the packet losses, time delays, and delay jitter, okay, in the communication network. So for this purpose, us control system theorists, we would like to have a good communication network. Okay, what is a good communication network? I will give you a hint. So you want to optimize the network in the sense that at least U is a delayed version of UC, and hopefully it's a constant delay, okay? And the same thing for Y. And I'm going to illustrate some of these things here. So, okay, how do we model these signals? So the command signal reaches there with a delay, and then possibly with a noise. Okay, so this is our model. Why do we do that and how do we do that is illustrated in this figure. So you see, you send the command signal UC, this is the blue line, and the red line is the U, how it gets there. So there are some packet losses, time delays, and quantization effects, etc. So if you define a slowly time varying delay, this one, you can, the rest, if you subtract the two, the rest is a noise, okay? Or actually, if the system is very good, very well designed, you can take a constant delay and add a little bit of more noise to the system, okay? So this is how we model it. And in our analysis, we dealt with time varying delays as well, but what I'm going to show today will consist of constant time delays. Okay, so this is going to be the dashed line, and the rest goes into the noise. Oh, okay. There are some abrupt changes possibly in the delay due to sudden changes in the cross traffic in the network, or there is a malicious attack. Somebody messes up with your network and cuts the signal transmission. So these fall into the domain of switched time delay systems. Again, we have had several works on this topic, but today I'm not going to go into those because they are very, very technical. So something you may recognize for those of you who are dealing with computer communication network, active queue management for congestion control uses this kind of technology. So there is a plant which is TCP and queue dynamics, for example, and the linear controller sees this plant, and S is the Laplace transform variable. So this is linear time invariant system representation. The rest can go into the noise, and you want to find a linear controller which stabilizes the feedback system. So I will come to stabilization issue a little later, okay? But you can see that this transfer function contains not only S, but there is e to the minus R0S. So this e to the minus R0S is a time delay, okay? And it appears in the numerator and denominator. So this falls into the category of retarded time delay systems in the control theory jargon. And interconnection of several time delay systems, you may have several components connected to each other, and between each of these components there may be time delays, and at the end you may get a transfer function which is a quasi-polynomial in the numerator and quasi-polynomial in the denominator. Okay, quasi-polynomial means that it's a polynomial in S and e to the minus HS. So these type of systems we are dealing with, mathematically speaking. Okay, so what are the robust control problems related to this? But before I define robust control, I have to define the objects I work with. So we work with plant. So it has an input and output. So this, I assume, is a linear transfer function and represented by the P of S, its transfer function. Okay. When we say that an input-output system is stable, if finite energy inputs lead to finite energy outputs, and the L2 induced norm of the operator is finite. Okay? For those of you who understood this, that's really great. But if you didn't understand, you can think of this P of S is a transfer function which is bounded and analytic in the right half plane. So it means it doesn't have any poles in the right half plane and on the imaginary axis. And it turns out that the norm energy amplification through the system is computed by the largest value of this transfer function on the right half plane, and by maximum modulus principle, it is achieved on the imaginary axis. So you just draw the Bode plot, find the peak value of the magnitude, that's your H infinity norm. Okay? In simplest term, it is this. Okay. So I defined an open loop system, stability is belonging to the class H infinity. Okay, so there are some special type of transfer functions. For example, the time delay I'm dealing with in today's talk is a transfer function e to the minus HS. So that is the delay term. Okay, so wherever you see this, the signal is delayed by an H amount in the transmission. And finite dimensional systems have rational transfer functions. So polynomial divided by another polynomial. But infinite dimensional systems have irrational transfer functions. Okay? So that is a complication when dealing with time delay systems. And I use the terminology inner function quite often later on in the talk. A function is inner if it is stable, first of all. So stable means it's in H infinity. And magnitude is constant 1 on the imaginary axis. So that's an inner function. Another thing I use quite often is the small gain theorem. So this is the fundamental theorem of robust control. What is it? let's say I have a stable system G here, and I connect in feedback a delta, an unknown transfer function, okay? So this feedback system is stable. In other words, transfer function from here to here is stable for all delta, okay? You look at all possible delta. If this small gain condition is satisfied. So the norm of G times delta should be less than 1, okay? So that we use later on quite frequently. So what is a feedback system? Typically, you have a plant and you want to design a controller, okay? So if you write down the signal equations here, the feedback is expressed like this, and the control action is expressed like this. And if you combine these two, you get the closed-loop transfer functions, okay? Sensitivity function, which is this, complementary sensitivity, controller times sensitivity, and plant times sensitivity. So the feedback system, we say, is stable if and only if all these three transfer functions are stable. Okay, so that's my definition of stability. And that imposes an important restriction now. If plant has a right half plane 0 or a pole, you cannot cancel it in the controller expression. So no right half plane pole 0 cancellation is allowed. Otherwise, what happens is either this guy or this guy will be unstable. You can easily show that. Okay, so one of the interesting robust control problems is strong stabilization. So feedback stabilization is find a controller C for a given plant such that all these transfer functions are stable. This is relatively an easy problem. There is also strong stability, that is, you want to find a controller stabilizing the feedback system, but itself should be stable. This is a hell of a difficult problem. It's unbelievably difficult problem, and I'll explain you later on. So the problem now amounts to the following. Let's summarize. You want to design a controller so that the feedback system is robustly stable. Robustly stable meaning considering the uncertainties that may be present in the system. And some performance objectives are met. Okay? Now, one of the important stability robustness measures is the delay margin. Okay. So, just to illustrate this, I'm going to give you a robotic example. Let's say you have a two-link robot, okay? This is free to move, this a bottom link. And at this link, when they join, there is a motor, okay? So you measure the position deviation from a certain point on link 2, and you send it over a network, and you design the controller, and you send the signal back, and that gives you the motor command signal. Okay, so this is like an elbow like this. Okay, so you just control it like this, and you want to stabilize it. So the objective is to keep it in the upright equilibrium point. Okay, question now is this. Before I say this, obviously this is an unstable, open loop unstable system. If you don't do any control, slightest perturbation will let it fall, right? This is even true for just one link, inverted pendulum, okay? Okay, so now, this is an unstable system, it's difficult to control. Moreover, you can ask the following question. What is the tolerable delay? So what is the amount of delay in the network or in the system you can tolerate? Let's say you designed a controller for this plant. How much delay can you add there? This is a very basic, fundamental stability robustness question. And this is the delay margin. Another difficult problem in robust feedback theory is optimization of this delay margin. So the question is this: can you find a controller which stabilizes the feedback system for the maximum allowable time delay? This problem is also very difficult. There are several papers published on it by now, okay? And we did look at this problem. Let's say you designed a controller. Can you add additional components to the controller to improve the delay margin, make it larger? So it was this paper. The other question related to this particular example is this. So there is a sensor here, okay? And it reads this deviation. And the location of the sensor is here, okay? So what is the optimal sensor location so that the controller that you are going to design to maximize the delay margin gives you the best delay margin? So this problem, we studied with my students and colleagues, and I'm going to present it on Monday in a workshop in Paris, okay? Okay, so we said that this plant was unstable. So I just want to take a breather here and give you some historical notes. Unstable systems are difficult to control. And when you design controllers, you have to respect instability. So there is a beautiful Bode lecture talk. This is an award given by IEEE Control System Society, and the very first award went to Günther Stein. And he gave this Bode lecture, and I don't think anybody can top this Bode lecture until now. And everybody talks about it. If you haven't seen it, I highly recommend, take a picture of this page and try to look for it on the IEEE Control System Society webpage. You know, a couple of years ago, remember Boeing 737 MAX 8 planes crashed, right? There were some discussion on why they crashed. And I was discussing with Abdullah Atalar, you know, what happened. I told him just to look at this thing. And he came back to me the next day and said, but this guy explained everything why these planes have crashed. You see? So I highly recommend it. Okay. But the main lesson from this particular talk should be that not only instability, but also you should respect the delay in the system. Okay? So you want to design your controller according to the delay in the loop, in the feedback loop. Okay. Okay, so now we are getting a little bit technical. There are several classical robust control problems. For example, the blue ones does not restrict the feedback controller to be stable. The red ones restrict the controller to be stable. The first problem is, given a plant, find a controller which stabilizes the system. Second problem, giving a weighting function and the plant, you want the controller which minimizes the weighted sensitivity function. And the mixed version of it, given W1, W2, you want to minimize the infinity norm of this closed loop transfer function. Okay. So the blue ones are solved. They are well-known techniques, and I'm going to show you the solution for this S2 towards the end of the talk, how it looks even for time delay systems, not just rational transfer functions. But this one is currently unsolved. Okay? So why sensitivity minimization? So when W is 1, inverse of the sensitivity is the distance on the Nyquist graph from -1 to the G of J omega. Okay, so you want to make this thing large for good robustness to perturbations in the gain and phase combined. Also for reference tracking, this is good. And why do we consider the second part? W2 times the complementary sensitivity less than 1 for such plants guarantee robust stability. Okay? I don't want to spend too much time on it. That's what it is. But let me give you the solution for the simple problem first, S0. Let's say you want to find a controller. By the way, how do we do it? The classical way of doing it in feedback control theory is design observer plus state feedback. I mean, everybody does that. We teach this in the undergraduate courses. Okay, but there is a different way of doing it using analytic interpolation. Okay, so if you can find a sensitivity function, which I call sensitivity function, which interpolates certain values in the right half plane to certain values given. Okay, so if you can find such a function, in particular, these are given here, and you can construct the controller this way. It solves the problem. And there is a solution here, and then there is also characterization of all stabilizing controllers here. I don't want to spend too much time on it. But now one-step extension of this interpolation is the solution to the sensitivity minimization problem, okay? So it is solved using Nevanlinna peak interpolation. So here you have W times S as F. So given certain points in the right half plane, and you want them to take certain values in the right half plane. Okay, so this is the interpolation conditions. And you want to find a function f such that the infinity norm should be as small as possible. And this is the Nevanlinna peak interpolation problem, and it has been solved long time ago in Walsh's book in 1935. There is an iterative solution to this. And this iterative solution has been used in control theory quite a lot, including my late PhD advisor, Alan Tannenbaum. He was the first one to put it in the control theory. Then later on, we had a one-shot, very easy solution rather than sequential solution. And later on, with my former PhD student, Veysel Yücesoy, we had a simplified, very, very simplified formula for the optimal interpolation. Now, this is true for finite dimensional system. What happens if there are time delays in the system? Okay, in that case, what we do is we do a co-prime factorization of the plant. So D of S and N of S are stable transfer functions. So D of S, the zeros of D, are the unstable poles of the plant. Okay? And the rest goes into N of S. This is how you construct. So these are co-prime in H infinity, meaning that N and D do not become zero at the same point in the right half plane. But it is very easy to construct such co-prime factorizations. I will give you an example. So for these problems, when N is infinite dimensional, for example, if it contains a time delay, then Nevanlinna peak does not help. You have to go to more complicated machinery in mathematics, which is called the Sarason's theorem or commutant lifting theorem of Nagy-Folyas. Okay? And the starting point is to do this factorization. Okay? Well, we have done this, let's see, 95, 2025, 30 years ago. It published in the book. What happens? Nobody reads it. Okay? Nobody reads it, nobody understands it. They all want a MATLAB code. You give the numbers and it shoots out the result, okay? So, okay, one of my former students wrote a MATLAB code, but again, nobody uses it. So, for this reason, we wrote another book where we explained step by step as if you are explaining to somebody you know very well, okay? Okay. Factorization example, and this is a plant example. So the plant is a quasi-polynomial divided by a quasi-polynomial. In order to do the factorization, first thing to do is to find the right half plane roots of the denominator, okay? So the denominator quasi-polynomial, what did we call? The roots of them are beta i's, okay, in the right half plane. By the way, there are software tools to do this by now, and very good software tools. And the right half plane zeros of the numerator are also computed. Then you construct P as P0 times P1, and it's finished. This guy is finite dimensional, this is infinite dimensional, and it is stable, by the way, because the roots of n of s are cancelled by the roots of m alpha at the same point, and the same thing here. Okay, so this is an example how we can do it and how we can solve these problems. Now, for strong stabilization, it's much, much more difficult, okay? So for the sake of argument, I have included the sensor here, H. Okay, so if P times H is stable, okay, the simplest controller to stabilize the system is 0. Don't do anything. 0 is a stable system, but obviously it is not an interesting thing. I mean, you want to do something. That's why you construct the feedback. The other thing is this. This is very, very important, actually. Aggressive design leads to unstable controllers, optimal controllers. So what you can say is that, okay, I have the solutions to the mixed sensitivity minimization problem without the controller constraint, okay? Let me solve it. And if it gives me a stable controller, optimal controller, great, we are lucky, okay? What happens is this. Even for stable plants, specific weights are given here, but don't read them, okay? There is a certain parameter. As you increase this parameter, the design becomes more aggressive, okay? Aggressive meaning that you want a very good performance from the system in terms of reference tracking or something like this, okay? So it turns out that when the delay increases and when the design becomes more aggressive, it is likely that you get an unstable optimal controllers, okay? So why strong stabilization? Maybe I go this very quickly. So Günther Stein's Bode lecture gives a very good argument for that, one thing. Offline testing of the open loop controller. Let's say you design the controller, you develop the algorithm, and you give it to somebody, okay? And it is going to be put in the aircraft. They will control the aircraft with this controller. They put it in the hardware. And they bring you the microcontroller, the box. They say, we implemented your algorithm here in this box. How do you trust this guy? Okay? So that's a very big challenging issue because you cannot check it offline, just alone, right? Because if it is really well implemented, it is supposed to be unstable. You give a test signal to it, it blows off. The only way to check it is to test it in the feedback loop with the plant. But then, if it doesn't work, you destroyed the airplane. Okay, so they were very reluctant to implement this. Another important thing is when the plant is stable, you don't want to use an unstable controller here because if there is, let's say, a malicious attack in the network here and cuts off your information, you don't want to give an unstable, unbounded signal here. So for, good security against malicious attacks or at least sensor failures, this is also good. There are a couple of other reasons, but let me skip them in the interest of time. Okay, strong stabilization methods. Basic fact about just the stabilization. So if I have a plant, rational plant, nth order, I can find at most nth order stabilizing controller. Very easy. observer plus state feedback. That's done, okay? But the question is now, what is SS0? Can I always find a strongly stabilizing controller? And unfortunately, the answer is no. The plant must satisfy a certain property called the parity interlacing property. Only under this condition, this is if and only if you can find a strongly stabilizing controller. So here, let me explain it this way. On the positive real axis, if you have zeros, between these zeros, you must have even number of poles. If you have an odd number of poles, like this, it's not satisfied. No, there is no way you can find a stable stabilizing controller. Okay, so in that case, you have to change the actuator locations, sensor locations, etc., whatever you need to do. More bad news. You see, this configuration does satisfy the parity interlacing property. As the imaginary part of these zeros go to 0, parity interlacing property is getting close to be violated. Okay? In that case, the minimum order of the strongly stabilizing controllers that you can use increases in an unbounded fashion. So that's a very, very difficult problem. So not only the number of poles and zeros in the right half plane, etc., but their locations also determine how difficult the problem is. Okay, so this problem is solved by what we call construction of a unit in H infinity satisfying certain interpolation conditions. I'm not going to bore you with the details, but believe me that there are procedures for that. But if you insert a degree or norm constraint for the unit, this is still an unsolved problem. And one solution is using Nevanlina peak interpolation. Let me skip this again. And under a certain sufficient condition, you can pose the unit construction problem to checking an H infinity norm condition. This is called the one block H infinity problem, and this is similar to S1 problem. And we know how to solve this, even for infinite dimensional systems, systems with time delays. But unfortunately, this is a sufficient condition because the unit that you are going to construct is 1 minus R minus NQ1. You know R, you know N, but then you design Q1, so you want to make the norm of this less than 1, so by small gain, it is satisfied. And unfortunately, this is just a sufficient condition, okay? And if you want to impose further norm bound on the controller gain, so that becomes an S2 problem, and again, we know how to solve this problem. And I'm going to show you the solution in a moment, okay? Robustness analysis, okay. Some people argue that designing controllers using interpolation is bad. Why? Because you think that the controller pole is located at 1, let's say. How do we know it's not 1.00001, right? So these kind of things play an important role. If that happens, then you introduce uncertainties in the numerator and denominator, okay? And in this case, you design a controller C, strongly stabilizing controller C, for N over D, nominal plant. And that gives you the nominal sensitivity and nominal complementary sensitivity. And if this norm is less than 1, it is stabilized for all such plants, strongly stabilized for all such plants. Okay? So, but trying to minimize the left-hand side here, using strongly stabilizing controllers for the nominal plant, again, is an unsolved problem. Okay? There are only sufficient conditions for it. Okay, so let me just give one example here. this one. So remember, we have done factorization for this plant. We have this. So what we do here is that we find a strongly stabilizing controller for this finite dimensional plant, C0, okay? Then C0 times P1 inverse strongly stabilizes because P1 and P1 inverse are stable, okay? But the problem is P1 is infinite dimensional. Exactly implementing it is difficult. So what you do is you approximate it by P1A inverse. But in that case, you change the closed-loop transfer functions, so you need to check the robustness condition. So if this condition is satisfied, then we have strong stability. So here is an example. I think P0 here in this case, fourth order. We have third order strongly stabilizing controller. We are lucky that the poles and zeros are not in bad places. And then an approximate P1A is constructed for the infinite dimensional P1. You see the match here is not really good in this frequency range, but that's not important because closed loop transfer function takes care of that. And this one becomes less than 1, so we are safe. For a small gain approach, I also have an example, but let me just skip this and mention a little bit about the solution of the S2 problem for infinite dimensional systems. So we explain how we do these inner outer factorizations for the plant, W1 and W2 rational given. Your optimal controller is in this form, okay? We have these controller pieces and their explanations in this book, 2018, and it's really a step-by-step construction and lots of examples for different kind of infinite dimensionalities, okay? The only infinite dimensional part is this one, and N0 inverse, possibly. So we approximate them, you get optimal H infinity controller solving the S2 problem. Now, if you have just a pure delay, just at that time here, pure delay, with a rational P0, if you are only interested in stabilization, you can use Smith predictor. This is a very classical way of designing controllers for time delay systems. It's a very clever idea. That is, your controller structure is this. K here stabilizes P0, okay? And K stabilizes P0 means this T0 is going to be stable automatically. And then there is a, oops, where did we go? Okay. There is a feedback internal to the controller. And this feedback contains the time delay part and P0 again. Okay? So, in this case, this such controller stabilizes the feedback system and gives me the closed loop transfer function is this, T0 times the delay, which this is really a huge, important result. It really must be appreciated because it's not really obvious. But the problem is, there are some exact cancellations when you do the feedback loop transfer function computations. So, how about robustness against plant uncertainty and delay mismatch? So people have criticized this a lot. And Smith basically is Otto J. Smith from UC Berkeley from the 1950s have proposed this. And since then, people have taken it and beaten to death, okay? But again, P0 here I use is the same P0 in the plant. How do I know it's exactly the same? Okay, so there may be uncertainty in it. This delay, come on. This delay here is the same delay here. How about there is a mismatch? Okay, so also when the plant P0 is unstable, this structure is not really applicable. So we look at the uncertain plant case. which contains really uncertainty. So there is a nominal P0 here. I'm allowed to use that one now because the uncertainty is captured in delta P. Same thing for the delay amount H. The uncertainty is also further captured in the delta P times Wm. So the Smith predictor changes very, very slightly. Previously, you had 1 here instead of H of S. You had 1 here, okay? So all you have to do is to find an H which is stable and satisfies these interpolation conditions and minimizes the H infinity norm of this. Again, this is a Navalny peak interpolation problem, and this is really great, solved. So we have an extension to multi-input, multi-output cases as well. So here is an example. You have a 3-input, 2-output system. M is like a delay, cross delays, etc. I mean, captures a lot of combinations. And P0 is a finite dimensional multi-input, multi-output system. So again, this class of systems can be captured. Again, the structure is this, same structure, and B is again in this form. But this time, because this is multi-input, multi-output, you have to do tangential Navalny peak interpolation, which is a little bit more complicated than the original one. Okay, so that's the result. And I'm going to present this result next Thursday in Porto. Okay, so in the Rocont seminar. Okay, so what are these? Open research problems. We have seen the solution to the optimal H infinity problem for S2, but SS2 is an unsolved problem. H infinity approximation of irrational transfer functions is a very valuable tool, but there is no optimal solution to this problem in the following sense. Let's say I give you an arbitrary stable transfer function, infinite dimensional, and I want an nth order approximation. What is the smallest norm you can get as the approximation error? Or I give you the approximation error, acceptable approximation error. What is the smallest degree stable approximation to it? These are unsolved problems. Really, mathematicians still play with them. For the same reason, fixed order stable H infinity control problem is an unsolved problem. I don't know if we can get a strongly stabilizing controller from the extended Smith predictor. In other words, from this structure, I would like to check whether this feedback loop, under which conditions it remains stable. This is also an interesting open problem. Extension of Smith predictor to multi-input, multi-output, and nonlinear systems. As I said, this is already done. So that's next week. Okay, so I think that's all I have to say. Thank you for your attention. Türkçe de alabiliriz. So if somebody doesn't understand Turkish or wants to feel more comfortable with English, I can take questions in English. Ama kendinizi Türkçe daha iyi ifade ediyorum derseniz Türkçe de soru alabiliriz.
First of all, thank you for making time for us to be here on your busy schedule, busy travel schedule. This was a very important talk, especially to me, where I try to approach these problems from the network side. I'm asking in English because there are people in the audience who may be interested in the question and the answer who don't speak Turkish. So now this is all your talk was in continuous time.
That's correct, yes.
I'm sure there's a discrete time version of the whole theory.
Let me just
Maybe not.
quick answer to that question. When you look at it in the discrete time, infinite dimensionality disappears. Time delay just becomes bunch of buffers.
Yes.
Okay, these are very simple, and you can have state space representations. You can use state variable, but when you use state space variable representation for time delays and then apply, classical techniques such as state feedback, observer design, etc., you lose the structure. So you lose the intuition. What is the effect of delay? How many taps you're gonna take? What is the sampling time, etc.? These are very, very open problems. Yeah.
Yeah, I can imagine. So my question maybe we'll try to dig into the open set of problems a little bit. So now, suppose, the continuous time version gives us a nice understanding of how it works. But now, consider the sampled time version.
Okay. Yeah.
Delay in networks is sometimes caused by queuing.
Yes, yes.
So this queuing is influenced by the rate at which those controller outputs are put into the queue. So then delay becomes not independent anymore.
Yes. This is
Because
depending
in the model,
on the input. Yeah.
One of the core things in the model was the delay was given. It was a given. It was not a result of the controller.
No. The delay is not a result of the controller here. It's the result of the network. But if you think about, we dealt with network designs also in the past using time delay models. But if you think about, active queue management, for example, there you see if you give more, the delay will increase.
So
yes.
Active queue management is a control problem just controlling the delay. Now you have a controller trying to control the system, the plant on the other side, but the samples, the period between samples generated by the controller, when they get queued, they in turn introduce delay.
Right? That is correct. So that's why that is why I said that network design should be excellent. Okay, so it's not like maybe I understand.
So what I'm trying to get at is, can the controller somehow also select which samples it's going to send, which samples it's going to hold, and generate samples accordingly?
That is correct. Yes, that's a good idea. Yes, but here my presentation did not deal with this question. I assume that whatever I send gets to the destination with a delay, and whatever that delay is, I assume that the network design people have taken care of this design in such a way that they handle the buffers, etc. So actually, you see, from my experience, if you always keep some queue in the routers, you can control the delay very well. It's not so the problem is when the buffer is full or getting close to being full, then the packets are dropped. These are more difficult problems. So the most important thing is to keep the buffer not full. Usually we set to 50% full, let's say.
Yeah, exactly.
But selecting the sampling time according to the control feedback you get from the system is a good idea. It may be worth trying. Yeah, thank you.
Thank you.
Murat?
Benim konum değil, çok güzel. Acaba can we generate you mentioned about the approximation of the irrational transfer functions in the under H infinity control. Is it possible to decompose those systems using the moduli spaces and then trying to solve for the problems under H infinity?
The answer, I don't know the answer to your question because I have not tried that. Maybe it is possible. But let me tell you something. This has been an open problem since the word H infinity has been introduced. Maybe, I don't know, in the 17th century, 16th century. So this is very, very interesting problem. There are some ideas. Let's say, Chebyshev has worked on it. And he has a theorem, Chebyshev equi-oscillation theorem. So people try to capture that. This may be related to what you are asking. İsmail, arkaya verir misin?
Thanks again. That was a great presentation. I just have a philosophical question. We have listened to so many AI presentations, like how AI is solving different types of problems that we used to solve with mathematics. Now, why do you think this area is specifically so challenging for AI that you're still trying to solve this with exact solutions like mathematics?
Why?
I
don't know.
No.
I don't know. Maybe if you give it to AI, it will shoot out a solution.
Do you think?
How? What the AI will do? Will it take all possible infinite dimensional approximations that has been done in the world so far and then try to improve on them? It is possible, yes, because if you find you give the artificial intelligence infinite dimensionality and you give an approximation to it and ask to improve it. I am 100% sure it will improve. Yes. But will it be optimal? I don't know.
Thank you.
First of all, thanks for the precious presentation. I am Serhat Karaman from Eskişehir Osman Gazi University. I am studying and researching the dynamics of the six-joint robot for the digital twin applications. You stated the robustness of the robotic system as an example in your slides. So I'm going to ask that what must be done when making the robotic system more robust, considering the singularity rule? And how does it work for the multi-joint robots or collaborative robots?
I'll give you a very short answer. I don't know.
Okay.
I don't know. I have no idea. You model the system and then you work with it. But my experience is that multi-joint robotic systems are highly nonlinear, and some nonlinear control techniques must be done. What I have shown here is at the upright equilibrium point, small perturbations, so you get a transfer function. But in general, it's not like that. So, for example, you have a swing-up problem. It swings down and then goes up and stays in the upright equilibrium point. These require nonlinear control techniques.
Thanks. I have one more question, if available. Okay. Beyond of kinematics, dynamics have too much effectiveness in any motion of robots because of their torque changes in their joints. So my second question goes on is, are there any strong stabilization techniques used when controlling the dynamics of the robot to monitor the system in runtime?
Again, I don't know. I'm not an expert on robotics. I cannot say much.
Okay, thank you.
Okay. Tayfun Hocam, let's take the last question. We already overpassed the coffee break.
Hocam ben Türkçe sorayım.
Sor tabii, buyur.
Müsaadenizle. Şimdi AI dışında, yapay zeka dışında gerçek matematik içeren gerçek zekalı bir şey görünce hoşuma gitti. Uykudan uyandım bazı yerlerde. Şöyle bir şey soracağım. Kontrolcü değilim. Tamamen sinyal işlemeci gibi düşünüyorum. Şimdi arada bir yerde gürültü olsaydı, o gürültünün de karakteristikleri farklı olsaydı, yani IID, white noise, beyaz gürültü falan değil de böyle ne bileyim pembe gürültüler, brown gürültüler falan olsaydı, bunlar nasıl etkilenirdi? Var gürültü V galiba ama...
Hocam burada şu V dediğimiz şey gürültü zaten.
Ama hiç karakteristiğini...
Karakteristiği de bak şöyle, şuralarda bir takım weight'ler seçiyoruz ya.
Evet.
W1 bak şurada. Okay. Bunlar işte yani istersen bunu gürültü olarak algılayabilirsin, ister referans olarak algılayabilirsin. Aynı şekilde bunları da robustness olarak algılayabilirsin. Bazen uncertainty, disturbance olarak koyabilirsin. Yani bu robust kontrolün standart tekniklerinden birisidir. Dolayısıyla eğer noise hakkında herhangi bir şey biliyorsan onu weight'e koyuyorsun. Ondan sonra devam ediyorsun.
Teşekkür ederim. Uyumuşum orada. Ayran.
Ya önemli değil. Bu zaten o şekilde anlatmadım. Peki teşekkürler. Herhalde ara alsak iyi olur. Teşekkürler.
Biz teşekkür ederiz. Uçağa binerken yükünüzü biraz ağırlaştırın.
Yapma ya. Ya bir dakika, sabah ne anlattım ben size diye. Siz yoktunuz orada ama.
Onların ismi yok. Keten tohumundan kurtuldunuz ama hocam bundan biraz zor. Şöyle ortaya